we're in the process of using our good friends, equilibrium and free body, to calculate internal member forces. Now, just to reinforce that point, I've come up with some really crap hand-drawn PowerPoints, but it was just to try and make a point. Please do tell me afterwards. I'd love some feedback, whether it was worthwhile making this point to you. Would love to know. Okay, I'm telling you, when you calculated your reactions, whether if it was a beam or a truss, it didn't matter, because all you were doing was free body diagrams and equilibrium. So if we consider our beam system, crank beam to the left here, I have a pin and a roller support, I have a horizontal load of 10 applied. So over here I would draw my two unknown reactions, and a roller I would draw my one unknown reaction here. Let's call that A. So AY, AX. Now, just from looking at this very quickly, hopefully you can all tell me what AX equals. 10. Okay, so that reaction there is 10. And taking moments at A, I have 10 times 5 going anti-clockwise. Can you see that? Yeah? Plus BY times 10. So from that we know that BY is equal to 5 kilonewton. And it's minus 5 kilonewton. Can you see that? So if I now draw my system here of forces only, leaving the structure out, I have a force here of 10. I have a reaction here of 5 down. So what's AY equal to? 5 up. And I have a horizontal reaction here of 10. And you can see by looking at that, you can see X and Y equilibrium quite easily. If you do take moments, you could see moment equilibrium. Now, to the right, I have a truss structure. It has a pin support and it has a roller support. And it has a load, a vertical load of 5 kilonewton applied. Now, if I just draw that system of forces here, I'll call this AY again, and AX, and I'll call this BX. So if I draw that system of forces here, I have a 5, I have an unknown BX, I have a 5 up here, I have an AY up, and I have drawn my AX to the left here. Now, back here in that first system, what I left off, sorry, I want pen colour, I want to change my pen colour. What I left off here was this height here was 5 metres, and that distance, horizontal distance, was 10 metres. Now, you can see to the right now I have this system of 4 forces, and if you look at my truss here, the horizontal distance is 10 and the vertical distance is 5 metres. So comparing these two systems here, tell me, what does AX equal? 10. What does AY equal? 5. We have the 5 down here. What does BX equal? 10. If you don't believe me, once again we could take moments at A. So over here, taking moments at A, I have 5 kilonewtons times 10 metres. It's going clockwise, so it's minus. And the way I've drawn BX is plus, so I have plus BX times 5 metres. So BX works out to be 10 kilonewtons. So different looking systems, because when you just pull the forces out of them, you can see the forces are lined up the same way. And in this instance here, this 5 here was a load applied, whereas over in this system here, that 5 there was a reaction. But it didn't matter because they're all forces. So if we now move on to our beams. Let's look at this cantilever system first of all. I have 10 kilonewtons down here. So hopefully you could all work out we have a resisting 10 kilonewtons up. Is there any horizontal force on this system? No. So there'll be 0 horizontal force here. But these two forces, because they're not lined up, create a couple, and that 10 is causing a moment, clockwise moment. So therefore, my reaction moment here would be equal to 10 times 30. So if I now just draw those forces as acting, I have a 10, that's 3 metres, and I have a moment here of 30. I'll put the units in here. Now moving on to my second diagram, I have a pin and a roller, and my loading this time is a 30 kilonewton. So if I call that end A, taking moments at A, I have 30, and then if I call this force here By, I'll have 30 anti-clockwise plus By times 3 equals 0, so By is equal to minus 10 kilonewtons. So drawing that in, that minus means it's a downward force, and I have my action here of 30 kilonewtons meters, and therefore this vertical force at A will be 10. So once again, can you see these two systems are identical? So whether it's a beam or a truss, or the systems could look different, a cantilever or a simply supported beam, they're the same. In this third diagram down here, I have a simply supported beam with a point load up of 14 kilonewtons. Taking moments at A here, can you imagine my C reaction here, is it upwards or downwards? Downwards. And it actually has a value when you do take moments. So you would say 2 times 14, take away this force times 7. You would get a reaction of 10 here and a downwards reaction of 4 kilonewton here. Now looking at that system now, I want to know what the internal member forces are at B. So my free body diagram here, I have a 10 kilonewton downward force here, and when I cut the beam, we know we have an unknown moment, shear force, and horizontal force. So what is our horizontal force equal to when we consider X equilibrium? 0. What is my vertical force here? Well, it's equal to minus 10, which means it's going upwards because that one's going down. And have a guess what my moment is equal to. Yep. Okay, so that 10 is pushing it clockwise, so we have a 30 here. Kilonewton meters. This time round, this 10 is a shear force, this 30 is an internal moment. But look again just at the system of forces, and that system of forces is identical. So the point I'm trying to make is calculating internal forces no harder than calculating reactions. Just to stress that point one more time, because I've thought of it, it's a bit messy. Again, this was the truss from the previous page. We had a 5 down here. When we worked out our reactions, I'll just do it in red, we got a reaction here, I believe, of 10 and a reaction up of 5. So if I now say, okay, I have to do a method of sections and cut through here. So my loading is, my reactions are 10 and 5. If I work out these 3 member forces using the method of sections, I would get a negative value, so I'll draw it in its true direction, a 10 there. I would get a force in here of 5 root 2, and I would get a force to the right of 5. So the inwards facing arrows means effectively that's a compression force, and that's a tension force. Now, let's see if I can create that same system of 5 forces. Okay, if I turn this support, I'll keep this support as a pin. This 10 kilonewton, well, that now becomes my roller. These 2 other forces here, well, if I apply a force down to the left and a force to the right, that's one's 5 and that one is 5 root 2. What do I have? Well, I have a resultant force down here of 5 kilonewtons. And as 5 kilonewtons as you're loading, lo and behold, you get a reaction here of 10, a force up here of 5, and a force reaction to the left of 10. So here's a method of sections that I could turn into a beam calculating reactions. We have the same forces. So when you do look at equilibrium, you can just remove the whole structure if you wish. We're doing the same, we're using the same tools over and over and over again to get you to calculate internal forces. Okay. Was that helpful or not? Tell me later. You're not going to tell me now. You can say no. I promise I won't go away and cry. Okay. We had started calculating internal member forces and I was using equilibrium. We finished off looking at this pin frame system, this three-pin arch, and calculated the internal member forces at an angle. The final case I wanted to do was to look at this triangular loading case. So we have come across triangular loading before when we looked at resultant forces. So the first thing we need to do here is calculate the reactions. We want to know the internal member forces at B. So whether I consider the left-hand side as a free body diagram or the right-hand side as my free body diagram, I need to know what my two reactions are, or either of them are. So the first thing we have to do is calculate reactions. So let's call that A, and since the middle is B, that's side C. So which free body diagram do you want to use, the one with the triangle or the one with the trapezoid? I prefer the one with the triangle. So considering that, we need to know what this reaction AY is equal to. So in order to calculate AY very quickly, where would we take moments? We would take moments at C. So taking moments at C, the first thing we need to do now is come up with our resultant, or our equivalent point load here, as a result of that triangular load. And I have drawn it off centre, because for a triangular load, the resultant force we know occurs a third from the high end or 2/3 from the zero end. So I've marked that distance in there now, 4 on 3. What is the value of that resultant? Well, it's a triangle, so it's half of this if it's a UDL load. So it's 0.6 kilonewtons per metre times 4 metres divided by 2. Or think of it as a triangle, half base times height. So that force there is 1.2 kilonewtons. So now, taking moments at C, I would have my force of 1.2 kilonewtons. Where is it acting? It's acting 4 on 3 metres away. It's causing anti-clockwise rotation, so it's plus. And the way I've drawn my AY, that causes clockwise rotation about C. So it would be minus 4 times AY, from which we get an AY reaction equal to, where on my page can I see that reaction? It's equal to 0.4 kilonewtons. And say to yourself, oh, would I expect it to be so small compared to my loading of 1.2? Yes. Okay, so we have our reaction now, and now we'll work on our free body diagram. 0.4 kilonewtons. I'm cutting the beam in the middle, so what is the value of this load here in the middle? It's 0 at the left support, it's 0.6 at the right support. If we cut it in the middle, this height here is 0.3. If we didn't cut it in the middle, you would just use similar triangles. So if I wanted to know what it was at 3 metres, I would just say similar triangles. 0.6 is to 4 metres, as this unknown value is to 3 metres. So I'd say 0.6 on 4 is equal to question mark on 3, and then that would tell me the height at any location along. Anyway, moving on. Here is our free body diagram. It is a stable structure, so it is in equilibrium. So once again, what am I going to do here? I'm going to do exactly the same thing as I did to calculate reactions. I'm going to come up with an equivalent point load here, and that equivalent point load is 0.3 kilonewtons per metre times 2 metres divided by 2, which is 0.3 kilonewtons. Where is that load acting? It's acting 2 on 3 away from my cut. Can you see? I'm not doing anything different. So now, I have all my forces noted, all my reactions noted, my 3 unknowns this time. When I calculated the reactions back here, we only had, oops, I didn't say that one was 0. Hopefully you can all appreciate there was no horizontal load applied here. So our AX reaction here was equal to 0. So here, in this case here, my 3 unknowns were forces. In this instance here, my 3 unknowns are a horizontal, vertical, and a moment. So forces in the x direction give me H as the only force is equal to 0. Forces in the y direction, I have my reaction of 0.4 up, my action of 0.3 down, minus V is equal to 0. So V works out to be equal to 0.1 kilonewton. Now taking moments, remember I said the best place to take moments is to take moments at the cut. You can take moments, we could do the same calculation taking moments at the support, the left support. However, then we would have V in our equation as well, and if we got V wrong, that would lead to M being wrong. So the easiest place to take moments is at the cut. So taking moments at the cut, I have my unknown M. That's what I'm trying to calculate, my unknown moment reaction. It's going anti-clockwise because I've drawn it anti-clockwise. Do you remember what what a positive moment is? A positive moment is a happy moment. A moment that causes your beam to bend like that is a positive moment. And the way I've currently applied that moment, okay, here is the reaction here. I've applied a moment that's going anti-clockwise, but can you see it's causing a happy face? If I were to draw the free body diagram on this other side here, I would draw my moment here clockwise, my shear force up, and my horizontal to the left. I'm drawing them all in the opposite directions to what I draw them on the left-hand side. And can you see, if now the support is on this side, the way I've drawn that moment is still causing a happy face. So that's how clockwise on the left, anti-clockwise on the right are a positive bending moment. However, when we come and consider equilibrium, well, equilibrium we use our Cartesian coordinates, that anti-clockwise is positive. So in this case, my moment is positive. If I was considering in my other free body diagram, I would say it was minus M. But the final value for M I would get would be a positive value. Anyway, I have M here. Then I have plus my load down of 0.3 times my distance of 2 metres on a third, minus my reaction of 0.4 times 2 metres. All of that equals 0. So my internal moment is 0.6 kilonewton metres. So we've calculated the internal member forces. But no different, we're not using any different a method than we use to calculate the reactions. But of course, when you calculate internals, there's always a moment you're looking for. Okay. Now, that's all very well and good. I have got my overheads, I realise, in the wrong order here. So I'll repeat this again. What you have to realise is moment is directly proportional to curvature. So when I apply a load over here, my beam is curving different amounts. So that means the value of my bending moment varies. If I cut it at 1 metre, 2 metre, 3 metre, 4 metre, 5 metres, I'll get all these different values for my moment. So what I need now is I need to draw a bending moment diagram. I need to draw a diagram of the bending moment, the value of the bending moment all along the beam. And since I'm doing the bending moment, I may as well draw a diagram of the value of the shear force all along the beam. And we call these shear force diagrams and bending moment diagrams. Shear forces being the easier thing, we'll start looking how to draw a shear force diagram. So, as I've just said, the shear force varies along the length of the beam. So we require a plot of the shear force along the length of the beam, which we call the shear force diagram. So, how do we plot these diagrams? Very, very simply. First of all, we calculate our reactions. In this example I've got up here, because my load is in the middle, it's symmetrical. My load down is W. My beam is symmetrical, my loading is symmetrically in the middle, so my two reactions here very quickly must be each equal to W on 2. Step 2, we know to calculate the shear force. What do? We create a free body diagram. So here we would create a free body diagram. Now in this instance here, cutting it before would give me the value of the shear force before, and then cutting it again after the point load would give me a different value of the shear force. For this particular example of a point load, I could cut it at any distance 0 up to the point load x. So between the distances of, the entire beam is L long, between the distance of x between 0 and L on 2, my shear force has a constant positive value. When I look at my shear force value after the point load, between the L on 2 and L length, it has a constant negative shear force value. So my shear force diagram looks like so. It has a constant value between 0 and L on 2, and it has the negative value between L on 2 and L. So here we have now an example of a uniformly distributed load on a simply supported beam. Once again, my loading is symmetrical, so my two reactions will be equal to 25 each. If I want to know the shear force at 3 metres, what do? I cut the beam there. I draw I've only been lazy here and drawn two unknowns because I know there's no horizontal force in there. I cut the beam, I look at all the forces in the y direction, and I calculate the value of the shear force. A more general case would be to cut it at x metres, where x, in this case, represents anything between 0 and 10 metres. So if I call that distance x there, what is the total load down here on my free body diagram now equal to? It's equal to 5 kilonewtons per metre times x metres. So now, let me just write that in red. So we're saying the total load down here is now 5x. So when I now look at equilibrium in the y direction, I have my 25 reaction up, my loading down, 5x minus v equals 0, and you can see now I have a mathematical expression for my shear force. So I don't have to bother calculating at 1 metre, 2 metre, 3 metre, 4 metre, 5 metre. I've come up with a mathematical expression, and if I plot that, it plots as this linear varying line. If we go look at our expression here, so when x is equal to 0, v is equal to 25. When x is equal to 5 metres, that's in the middle, v is equal to 0. When x is equal to 10 metres, v is equal to minus 25. So that is just this plot here. So okay, so we can come up with general mathematical expressions and calculate shear anywhere in the beam. An even easier way, where we don't use free body diagrams at all, is what we call the diagrammatic method, okay, is to calculate your reactions. Don't bother what's a positive and what's a negative value, so don't use the positive or negative sign of the shear force. Start from the left-hand support and follow the magnitude and the direction of the vertical reactions and loads. So in this point load case originally, remember our load was W on 2, our reaction. So a shear force diagram, we start at the left-hand support, we step up a value of W on 2. Now, as we move along this beam, nothing happens. So we just move horizontally across this beam. Now, we're following the load. So suddenly, we step down. There's a point load here, a value of W. And that takes us from plus W on 2 to minus W on 2. As we continue moving along this beam, we don't hit any more vertical loads, so we just remain constant. And when we get to the end, we end up at 0, which is what we want to do, because all the forces in the y direction should equal 0. So now looking at the case of the uniformly distributed load, we start at the left-hand support. Our reaction is 25, so we step up a value of 25. Now as you move along the beam, the load is reducing. How much is it reducing by? 5 kilonewtons per metre. Every metre you move out, the load is reducing by 5 kilonewtons. So you know that is a linear drop. So by the time you get to the other end, it's dropped by 50. So this step in here this time is 50 kilonewtons. And then when you get to the other end, you hit the reaction, and you step back up, and you end up at 0. And that is how you plot a shear force diagram. So, why did I bother teaching you the equilibrium free body diagram way? Because you need to know and understand equilibrium and free body diagrams. Can you do it a quicker way? If you want to know the shear force throughout the beam, yes, just plot the diagram. So what you need to remember is the shear force diagram, when you're dealing with a horizontal beam, all it is a plot of the forces in the y direction. The shear force diagram is horizontal unless there is some sort of load applied. And the shear force has to end up at 0. If you don't end up at 0, you're saying all the forces in the y direction don't equal 0. You don't have equilibrium. Fair enough? Excellent. Draw the shear force diagram for me. Do it in your head. Don't yawn out loud so I can hear you. Makes me feel like I'm boring you, and I know I can't be doing that. Symmetrical loading, you know straight away what the two reactions are. They're equal. We got something drawn? We start at the left-hand side. We step up a value of 150. As we move along the beam, nothing happens, there's no load, so we move horizontally across. We hit a 100-point load, so we step down to 50. We move along the beam, no change. So this drop here is our 100 kilonewtons. In the middle of the beam, we drop another 100. So we drop down to minus 50. We move across. We drop down another 100 to 150. We move across, and then we step up. And you've now drawn your first shear force diagram. So you should be very happy with yourselves. So what does that mean? If I were to cut the beam here and asked you what the shear force was there, you would look at the diagram and say the value of the shear force is plus 50. What is plus? Plus is where the two shear forces cause an anti-clockwise rotation. If I, however, were then to cut the beam further along the beam, so that relates to that location. If I were to cut the beam in here at this location, my shear force is now minus 50. So instead of my two forces causing anti-clockwise, that would mean my two shear forces We're causing clockwise rotation. So that's what the plus and the minus mean. Yeah? Let's do a harder one. You ready for a harder one? Because that was so easy. Do that one. If I can find it here. Shall I give you the reactions? Do you think you can all calculate reactions? Yeah? This reaction here, 333. This reaction here, 66. Start at the left-hand side. Now, if you can't calculate those reactions, that's all right. But you need to go to the help desk and seek some help, or you need to go home and not go out this weekend and study really hard. Okay, shear force diagram. We start at the left-hand end. We start at 0. Oops, got the wrong colour. We step down a value of 100. Now what happens here? Effectively we're stepping up 300 and then coming down 100. So that brings us up to a value of 133.3. So we are effectively coming up and coming down, but those two forces, the loading of 100 is cancelling out straight away with that reaction. So we just step up to 133. So that step up there was 233, which is the difference of 133 minus 100. We move horizontally across. We step down 100 to 33. We move across. We step down a further 100 to 66 minus. We move across. Now, if at this point in time you're working beautifully and you say, I'm down at 66, and you look at your reaction and your reaction is equal to 80, then you know you've made a mistake somewhere, okay? That reaction has to bring you back up to 0. No one ever gets their shear force diagrams wrong. I'm being positive here. Bending moment diagrams, you stuff up. We'll start small and work out big. Not hard? Okay. Oops, I put them in there. Okay. Here we go. There's a uniformly distributed load on there. I've given you the reactions already. There you go. I've done all the hard work for you. I think I meant to get a mic and run up and down the stairs and see how you're going, but I won't if that's okay. Meant to make it more exciting for you. Had enough time? Yeah? No? Okay. You can be messy like me. You don't have to draw perfectly straight lines. Enough time? Okay. So we start at the left-hand side. We step up a value of 35. There's no load change. We move horizontally across. We hit our point load of 30. That brings us down to a value of 5. And now as we move along the beam load is reducing by 20 kilonewtons. Every metre you move along the beam, it reduces by 20 kilonewtons. So the total drop here is 80. So therefore I'm going to go from a value of 5 down to a value of 75, which happens to be equal to what my reaction is equal to, so I'm happy. So that drop in there is equal to 80. Now that, in a nutshell, I can make these things look harder and harder and harder, but that's it. You get a point load. Wherever you see a point load, you will see a step in your shear force diagram. Shh. Wherever you see a uniformly distributed load, you see a linear drop. Oh, one example I haven't done now. How about I do that now? I have a moment applied here on a simply supported beam. People don't know what that looks like. Can you be a support for me? So what I'm saying is I am applying a moment like that. So that's the sort of deflected shape I'd get. I'll draw it up on the overhead. So let's say this beam is 10 metres, 5 and 5, and my moment in the middle is 10 kilonewton metres. Can you tell me what my reaction here? On this side here, is it going to be an up or a down reaction? My moment is causing it to rotate like that. So to stop that rotation, I'm going to pull this side down. So my reaction here will be downwards. What will the value of it be? Taking moments here at A, I have a moment of 10. What's that reaction equal to? Okay? I'll call that AY. I've drawn it down anyway, so this one we know will be up 1. So if I take moments at B, they equal 0. My applied moment is 10 is going clockwise, so it's minus 10. And then I have my reaction AY, perpendicular distance from B is 10 metres. The way that's drawn, that's going anti-clockwise, so therefore this AY reaction is equal to 1. Okay, so there is my loading and my reactions. What does my shear force diagram look like? Again, you don't panic. I follow my loads. I step down 1. My shear force diagram is a plot of vertical forces. Is my moment a vertical force? No. I step down 1, I move across, and I step up 1. So whenever you have an applied moment here, nothing happens in your shear force diagram because you are plotting vertical forces in your shear force diagram. Okay, that's the relatively easy bit. Now we get a bit more complicated, but we can cope. You're all bright. And all it is free body diagrams and equilibrium, and a little bit more now. So now it's a little bit more, okay? Ready to move on? Do we need a break yet? Okay, I'll give you a 3-minute break. I can't cope with 5, I get bored. If anyone has any project questions or any questions about that, I'm looking at the clock. We'll start at 1:48. Yes.
I just have a couple of quick project questions. Do we need to consider loads perpendicular to the trusses, like cross bracing or anything?
When I said, remember when I said when you've got steel, you calculate the weight of your truss and then
Yeah.
you increase that by 20%
Yeah.
to
So
allow for
that's
any
allowed
of
for
the
things like
extra
that.
ancillary steel.
So we don't have to worry about, it's just the trusses just having vertical
It's
courses as stick
enough that you
diagrams.
design a truss, that's excellent.
And then the other thing was just the lift, was with the roof, live loadings.
Yep.
I found a formula, the standards had a formula on it.
Yeah.
Let's introduce a relatively high,
You're not using something else.
what area is that? Because
It's a tape out.
to the area of the typing. I just wanted that, because I wasn't sure, because it said that, the footnote didn't really make clear what the area was. Thank you, just wanted to check.
Is there something we can look at for like formatting, just like how the document, how the main report is meant to work, even if it's just like a previous like project?
There's something in the unit guide about what's expected in terms of production. You can type it, you can handwrite it.
I keep looking at it with my group and we're like, we don't know how to present this information. Like, it just seems like doing calculations, then creating a theory, and then
No,
how
that's
is
why
that theory wrong?
if you look in the brief, it says, so you should have like an introduction. So you should have an introduction. And then your next week, what did you do? You went to site. You went to site. So after your introduction, you should have a section of geometry. You went to site. You went to site. And you went to boom.com. Here's a figure. Yeah? What did you do next? Next, load it. There should be assumptions somewhere in here. Load it. Okay? What do you want to use for ultimate stage? Dead weight plus live load. Dead weight comprised of
It's just
go to the appendix, calculations. The final total dead load was this number. Yeah? The live load. We went to S1170 buffer. We looked in loading for a P. It was this. Okay? So you can say, look into the appendix for all the calculations, but here is the structure with our final loads applied as point loads to each joint.
and then you just write.
And then you do, next you do analysis. Okay? You do analysis for the appendix and calculations. Here are the results. So you have a diagram showing all the internal forces. Okay? You can make comment. As you can see, the forces here in compression, forces here in tension, the ability to smaller, done. No bleeding, stop, no crack. Don't want cracking. That's just what's necessary. Yeah? So the designing, here compression, blah blah. For appendix, these are the two columns we use. Here are our final results. Yeah?
Where did this 0.3 come from?
0.3. So this is when I cut it. Yeah? Now, up here, it was consistent. So don't go from there now. Yeah? Now this is from the plate over here. So it's my plate times height. 3.3 times 2 divided by 2 is 28. That's halfway. So if I write, does that mean something to you based on how you talk? Or you can just say, this is if I assume it is unit, the load will be 0.6 times 0.3. But I've only got half of that. Yeah? So I divide by 2. So you can look at it that way, or just a triangle not based on height.
Since everything is on since we found like some of the resources.
Yeah. I've got 0 load over here, I've got 0.6 kilometres in here.
So this is a point
No, it's here. So at this point here, I've got my 3 coming in here, at this point here, I've got my 4 coming in here. Okay, we've got lots of questions. Okay, I'll give you 5 minutes. I've got lots of questions.
Yeah, quick one. We found a video less. Like I said, we put on the joints and they both come. I'm thinking should the reaction be the same amount? Should it be stationary? Stable? Yeah.
So the reaction.
Yeah.
You're doing dynamics. Who's the other one you were doing?
And then we have enough information to find out how much cost of each one. Sure. Yeah. Yeah, because I mean,
This is
so if it goes down like that, and there's
Is
reaction.
that your middle?
easy on toes.
No, it's this one. Wouldn't that be W2?
Oh, at the end, yeah. Okay, so let's call these. I'll call these P, P,
Have a mid-semester.
So in this case, my total reaction is 1, 2, 3, 4, 5 P. So these reactions here are 2.5 P each, and that's 2.5 P each.
Yeah, for the graph, when we draw it, you have to specify which side you're taking it from.
Always from the left. Yeah, always from the left. Shear diagram, always from the left. Can you ask me that later, after? Yep. Okay. Okay, so that was the shear force diagram. Hard? No. Was that easy? Easy. Okay, now bending moment diagram. A little more complicated, but we can do it. So let's just go over again. What is a bending moment? A bending moment is an internal action which causes a beam to curve. So you'll see these in the tube class. It's a bit hard to show them to you now, but a very useful relationship, which I've already mentioned, which can aid in the drawing of your bending moment diagram, is the fact that moment is directly proportional to curvature. So by thinking how is the beam deflecting and curving, you can actually learn something about the bending moment. So I have here my simply supported beam, and I put a point load in the middle. And if you do look at the grids on here, when I say something's curving, what I mean is that square grid now starts looking like that, okay? It's getting smaller at the top and bigger at the bottom. So if you look at this square grid here, and you'll get it to look at it in the tube class, it's a bit, I won't bother passing one of these around now. Can you see any curvature happening here at the support? No, our grid stays as rectangular. So the internal moment in the beam there is 0, which it should be at a pin support. Because if I was drawing a free body diagram with a pin load, we know the reaction here is only vertical. So if I consider a little free body diagram, there's my reaction here, and say I'm cutting at 0.01 millimetres away, what would this internal moment be equal to? It would be equal to my reaction times 0.01, that's millimetres. So if we work in metres, 0.0001, so effectively 0. So you can see, you can imagine no curve in there, no moment. Where do we have maximum curvature? In the middle of the beam. So our bending moment will be maximum in the middle of the beam. So I have the next case, which I won't pull up yet, even though you've all got copies of it anyway. Cantilever. Where do you see the most curvature? People close up. Where is the grid? At the support. At the end here, I haven't put a point load on, but at the point loading, the grid stays rectangular. So for a cantilever, 0 curvature at the end. The curvature increases as you move along. High curvature, maximum curvature at the support. So please, when you draw your bending moment diagrams for a cantilever, don't draw maximum moment at the tip of the cantilever. That's where the moment will be 0. The only time the moment won't be 0 there is if you actually apply a moment. Okay, so now you go, okay, I can see the way something curves. The way it curves, I can imagine there's a lot of moment where it's curving a lot. So because curvature varies as you move along the beam, your bending moment varies as well, so we need a bending moment diagram, which is just a plot of the bending moment along the beam. It's not constant now. Remember back to trusses. For trusses it was beautiful. Because for trusses you wanted to know what a member force was. The member force in this truss is constant compression or tension throughout the length of the member. So in terms of a free body diagram, it doesn't matter if I draw a little one or a big one. When I draw my free body diagram, because my arrows were only axial, it didn't affect it. With my bending moment diagram, if I draw my free body diagram here or my free body diagram here, it affects it because my bending moment varies along the beam. So let's go back, just to simple numbers. Find the bending moment. How do we find the bending moment? We know what a positive bending moment is. We draw our cut, anti-clockwise if we consider left of the cut, clockwise if we consider right. Now here's the rule with the bending moment. Always draw your bending moment on the side of the beam in tension or stretching. So when I load this up with my chin and look like an idiot here, which side of my beam is in tension? The bottom. So I know when I come to draw my bending moment diagram, it is going to be under the line. If I have a cantilever and I load it like so, which side of my beam is stretching, the top or the bottom? The top. So I know my bending moment, when I come to draw it, I will draw it on the top. So, if I have a beam loaded and it creates that shape, what's my bending moment going to look like? I don't know what shape my bending moment has yet, but I know I'm going to be drawing it on the bottom, because that side is in tension on the bottom, and then I'm going to draw it on the top. So what do we call the point between, where it's on the bottom and on the top? What do we call that point there? Point of inflection. Your bending moment always passes through zero at a point of inflection, because we always draw our bending moment on the tension side of the beam. So if I ask you, as I always do, where is the point of inflection in your deflected shape, you will find the point where your bending moment passes through zero. So always put the bending moment on the tension side of the beam. So when a beam is sagging, we call this positive. So when a beam is hogging, it's negative. So what that means is when we plot bending moment, we plot it positive down. That's different to what we're used to. We always draw positive up. Now we're going to draw positive down. Now once you get used to this, it's not a problem. If you're a conscientious student and you go to use the textbook Hibbler, they draw their bending moments upside down. They draw positive up. Okay? So why don't we draw positive up? Because all the computer packages draw positive on the bottom. So we're teaching you how to do it. So when you see a printout from the computer package, it won't look upside down to you. But be aware, if you do further work using the textbook, just flip their bending moments on the horizontal axis. If you draw it upside down in the test, in the exam, you'll lose a small mark. Okay? Because you're not using the sign convention you were taught, which is to draw it on the positive side of the beam, the side of the beam in tension. Shear force, positive up. Bending moment, when we plot it, positive down. Okay. Here, we want to know the bending moment in the beam, so we know how to cut the beam and calculate it. We're going to look at calculating it at the ends, at the mid-span, and at quarter span. So we're going to be looking at calculating the bending moment here, 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 at 1, 2, 3, 4, 5 locations. What's the bending moment equal to at my two end spans? 0. Beautiful. You already know. At the end spans, simple supports. My bending moment is 0. If I, however, had a system that looked like that, where is my bending moment 0 here? Is it 0 at A, B, C? It's 0 at A, it's 0 at C, but my beam runs continuous over that support. So can you imagine how this thing is deflecting? This beam here is deflecting. It can't deflect here at the support, it can't deflect here at the support, so it's deflecting like that. Sorry, I meant to choose red. My beam is curving here, is it not? If it's curving, there's a moment there. Okay, so we've got the last two. At quarter spans, what do we want to know? We want to know the value of the moment. We cut the beam there. We calculate the value of the moment by taking moments at the cut here. So I have M, then my force here is P on 2, my distance L on 4, so I get the value of the moment. Always take moments at the cut, okay? Remember that. At mid-span, I want to know the value of the moment. I cut it at the mid-span. When it comes to taking moments here, I take moments at the mid-span, I get the value of my moment. I do the same thing at 3/4 span, I get the value of the moment. And now, shear force diagram, for this case, we've already drawn. We know what it looks like. What's our bending moment diagram look like? We don't know yet. However, we have 1, 2, 3, 4, 5 values for it. So, I've drawn a squiggly line here. We don't know what shape it is yet. But we're going to know that soon enough. Why did I know to draw my bending moment below? Because looking at my deflected shape, this T here means I have tension on the underside. I've drawn the T on the side of the beam. Because I have tension on the underside of the beam throughout, I know my bending moment is drawn below the line. Okay, so we want to come up with a quick way to draw, to fill in the gaps between these points. So just as we did with the shear force, cutting it at a distance x, we're going to cut it at a distance x, and we're going to come up with an expression for our bending moments in terms of x. Okay? So for this example with the point load in the middle, we would have to consider a free body diagram before the point load and a free body diagram after the point load. So coming up with a free body diagram before the point load, taking moments at the cut, I have m, then I have my point load p on 2 times x. So can you see here my bending moment is linear. When I do the same thing after the point load, I'm taking moments here at the cut. I have m. Oops, sorry. Where's my pen? I have m here. Then this load here represents my reaction force, P on 2 times x. Then my loading of P kilonewtons, well, if that distance is x, and we know that distance is L on 2, so this distance in here must just be equal to x minus L on 2. So I have my force, and now I have my expression for my moment. I have two mathematical expressions. This is how they plot. So I did that for the shear force, and I said, now there's an even easier way. We'll learn how to draw the bending moment. So we'll do that now. But you can do it by coming up with expressions for your bending moment. That's before I show you the easy way. Look at the uniformly distributed load case. Can you come up with the expression for the moment, cutting it at a distance x? If you've got the notes in front of you, don't look at them. Okay? Here's my free body diagram. I've cut it at a distance x, and I want you to take moments at the cut. Now, taking moments at the cut now, tell me what is my resultant load down here equal to? Yep. This force here is 5x. Where is it acting? In the middle? In the middle of x. So this distance in here must be x on 2. So, if we now take moments here, taking moments here, I should have said at the cut. What have I got? I've got m, my moment. I have my reaction at 25 times my distance x. This 5x is my load down, my distance is x on 2, and I have an expression here for my moment. It's now, you can see a quadratic, some sort of parabola. When x is 0, what's my moment equal to? 0. We know my moment is 0 at a pin support, don't we? 10 metres along, substituting 10 in there. 10 squared is 100 times 5. 500 divided by 2 is 250. Take that away from 250, your moment is 0. So what we've come up with here is our bending moment diagram. So there's the mathematical expression we got for it. Yes? What have I done wrong there? I've had that, oh, you're right, that should be plus in there, because that's going clockwise. And that should have been, oh, what have I done? Oh, hang on, no, my moment is clockwise. No, that's right, yeah, that should be minus, And that should be plus. Once again, oh yes, I put that in there to check if you're awake. Or what I'll do, rather than change those two signs, I'll just put in, no, we'll do that. Yep, they should be that way round. Okay? Thanks for that. I'll have to change that one. So here is what our shape looks like. So that's all very well and good. And sorry, in the middle of the beam, looking at that expression here, 25x, in the middle of the beam, if you consider the case of a uniformly distributed load on a simply supported beam of length L, the bending moment in the middle of the beam is WL squared on 8. Does anyone know a structural engineer? Go home tonight and go, what is the bending moment in the middle of a simply supported beam with a uniformly distributed load on it? And they'll say WL squared on 8. Because that's what you remember, WL squared on 8. Okay? So you don't bother, when you get these in the workforce, you're designing it by hand. You haven't bothered turning the computer on in the office. It's a simply supported beam. You don't have to do anything. You just go WL squared on 8, that's my maximum moment, done. And then you can design based on that. So that's something to remember. In a job interview, I've heard of cases in job interviews where, as well as saying, oh, how did you do, what do you like, blah, 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 what do you want to do in life, they've said, can you draw this bending moment diagram? And a lot of people can't. And this particular person could, and they got the job. So, WL squared on 8, remember that. Now, when we calculated that expression for the bending moment, for the point load case, we got two equations, didn't we? So wherever you have a point load applied here, how many equations would we require for our bending moment? 5. That's a bit of a drag. So a simpler way to do it is to create a free body diagram based on using singularity functions. Have you come across these before? They're also called Macaulay's brackets. No? Very beautiful, simple bit of maths here. Singularity functions or singularity brackets and Macaulay brackets are used to describe discontinuous functions, such as beam bending moments in one equation. Using this fact, what we do is when we have an x minus something term, we put it in pointy brackets. And that's telling us, okay, we're using singularity brackets. And the way these brackets work is, if the term in the bracket is negative, so if this term here, x less than a, means if it's negative, we set that value to 0. And if it's positive, it just becomes a normal positive value. So when you have these brackets, you never expand them. Because if you expand them, you remove the function, the ability to turn them on and off, to make them appear 0. So, let's go back to that point load case now. I'm going to cut my beam as far left as possible. This time round, when I have my x minus term, it's in my pointy brackets. So when I cut the beam and take moments, I get this expression here, m minus p on 2 times x plus this p at load acting times the yellow bracketed form. And this expression here now represents the bending moment for the entire beam. So how does that work? Let's have a look. When x is less than L on 2, this term is negative, it disappears. When x is L on 2, it means I've cut the beam through there. When I've cut the beam in this region, have I come across the point load yet? No. So that's why it disappears. So you can see here, this is the previous expression we got, cutting it before the point load. The expression here is what we got after the point load. Here is my general expression. When x is less than L on 2, this term here simplifies down. My moment simplifies down to the first expression. When it's greater than L on 2, I end up getting the identical expression. So instead of requiring, with 5 point loads, 5 expressions, you can now come up with one expression valid for the whole beam. I'll get you to do that now. Can you? It says determine the bending moment diagram. I want you to cut the beam here. Well, you can determine that using, hang on, okay, Determine the bending moment diagram equation. So you are going to, our reactions here are 150 and 150. You are going to cut the beam as far right as possible and consider that as your free body diagram. So we're now cutting it a distance x. So this distance in here is x minus 2 in my singularity brackets. This distance in here is x minus 4. And that final distance in here is x minus 6. So come up with an expression. I cut the beam, and there's my moment that I'm after. I'm going to show you an even easier way. The reason I'm showing you this way first is you need to know how to come up with an expression, a general expression for your moment, because we use that when we calculate deflections. So you have to know how to do it this way too, but I will show you an easier way. Take your moments at the cut. I have m minus 150x plus 100 Can you see how I got that? Just force times distance, force times distance. So the general expression for my moment looks like that. Does that all make sense to people? Now these brackets have the ability to turn themselves off and on. So when x is between 2 and 0 metres, that's where I'm cutting the beam before any point laid on there. What is my expression for my moment equal to? It's equal to 150x. All my other terms cancel out. Can you see that? And if you do look at your free body diagram, can you see that's exactly what you would have got? When my expression is between 2 and 4, my bending moment is equal to 150x minus 100 x minus 2. Oops. So can you see my expression grows in size as you move along the beam? Let me just see if I've got another page. Okay, now if we draw that shape, between 0 and 2, my bending moment is 150x. There's that line there. So So my bending moment has a value here of 300. So that's the expression for that line there. Now in this second range here, when x is equal to 2, what's my moment equal to? It's equal to 150 times 2, which is 300. That places me at that point there. When x is equal to 4, what's my moment equal to? 150 times 4 minus 100 times 2, and that gives me a value of 400. So it takes me as a straight line, as a linear varying line, to that point there, which is 400. And if you continue plotting all of these, you get a bending moment. These are all meant to be straight lines. That looks like so. And the beauty of it is that those 4 lines there, if I asked you to define them, you would have said between there and there it equals that, between there and there it equals that. You can do that all with just a single one equation now. That equation has discontinuities in it. Okay? Isn't that beautiful? You used to always go, oh, there's a change, I have to come up with a different range and have to come up with a different equation. You don't have to do it. So that's because of this ability to turn on and off things. Okay. Shall I show you something? I'll show you something and then, or do you want to have a go at, hey, come up with one more equation. Here. We've done the shear force diagram for this already. Now I will give you time and everyone have a go. You are going to cut the beam as far right as possible. So you are going to come up with your general expression for your bending moment diagram. Cutting it at distance x. So I want a general expression for that moment. Squiggle there because you need to know what the equivalent point load is down there. And what is that equivalent point load equal to? No, it's not 80. You have to look at your free body diagram now. So it's 20 kilonewtons per metre acting over a distance of x minus 4. Where is it acting? No? It's acting in the middle of that region. So what's this distance here equal to? X minus 4 on 2. So it's saying I'm going to teach you more than free body diagrams and equilibrium. What are we just doing now? Free body diagrams and equilibrium again. You can't get away from them. There are x's in there now, but x minus 6. Why 6? No, because this distance is x, see? X now represents anything between 0 and 8. Because we're using singularity functions, we're going to come up with one expression valid for the whole beam. So I don't think I'm telling you any secrets if I go minus 35x plus 30 x minus 4. And what's my third term? My load, we said 20 x minus 4 is my force. So who got that? Lie to me and say, yes, we all got that, Lizzie. Yeah? And then after the test, I'm going to shake my head and go, no, they lied to me. Okay, so look at our expression. It's linear, it's a parabola, it's a combination of everything. So, draw your bending moment diagram shape in here. I'll write the expression. Remember, these bracketed terms now are all singularity brackets. Whenever the term in the bracket is negative, it disappears. So between x and 4 metres, what's the expression for my bending moment? Just a straight line. So if I draw that now, because I'm drawing positive down, remember? The value here, $140. If you do then plot all the points, you can see now it's a quadratic shape. If you do plot them all, you end up getting a shape like that. So that expression and this expression in here is effectively that full thing. Now, because we're in the range of, within this range here, we're in the range of between 4 and 8, where these bracketed terms won't become 0, we can therefore expand all our brackets and we end up getting the expression minus 10x squared plus 85x minus 40. So that's just expanding out all that bracket because we're not in the range where those brackets can go negative, then we can expand them. I'm going to show you an easy way anyway. If you get that, when we do deflections in week 10, if you don't get it yet, don't worry, I'll go over it again in week 10. But what I'll do after I show you my interesting thing is I'll then show you an easy way to draw a bending moment diagram using your shear force diagram. Okay. What happens when you can't draw a Benny moment diagram? Well, not true. What we have here is a department store, Sampoon department store in Korea. That area you're looking at there is 61.6 metres by 50.4 metres. 4 or 5 stories, the whole thing collapsed. On June 29, 1995, in just a few minutes, the 5-storey department store building in Seoul collapsed into its 4 basement levels. Over 600 people died and over 400 were injured. What happened and why? I apologise for appearing to show all these failures occurring in other countries. It's just that certain countries have less stringent regulations, and so basically this is what happens when regulations aren't so stringent. This is what can happen. What happened? There would once again, no single reason triggered the collapse. However, overloading of the roof caused the punch-in shear failure of one of the top highly stressed column heads. The load then, up here, shed onto the lower floor, which in turn was overloaded, leading to progressive failure of the entire building. So what we had was, we had a department store that the owner wanted to expand. And they wanted to put a new floor on it, and they wanted to put air conditioning, water cooling towers on the top. So he went to the engineers and said, I want some water cooling towers, full of water tanks up on the top. And they did some calculations and they said no. Too much load. Can't handle the load. So what did he do? He ignored them. He sacked them. So the disaster was blamed on a combination of design errors, shoddy construction and maintenance. First thing that went wrong was the assumed design roof dead load self-weight. It was designed to be a 60mm thick slab. But when they went to look at it after it failed, they discovered it was actually 150, in places 280mm thick slab. So you know from your loading calculations on your truss, they calculated the weight of a 60mm thick slab, it was 150mm thick slab. As well as that, when they went to look at the engineering drawings, some of the columns were designed to be 800mm, but when they looked at what was there, they were only built to 600mm diameter. Steel reinforcement, they found, was positioned incorrectly, and as I said, the owner wanted to put more load on the top. He added a further floor with rooftop cooling towers as part of the conversion into a restaurant. The original contractors objected, but they were fired and replaced. So did this happen suddenly? No, there were signs of this eventual failure happening. Severe cracking in the roof slab was noticed weeks before failure. Water started to leak from the cooling towers. There was enough movement to cause these cooling towers to distort. They started leaking. The owner responsible, what was his response? He said, okay, move all the expensive merchandise down from the 5th floor to the ground floor. And that was it. So he was jailed for 10 years, his son for 7 years. I think that's not very much when you consider 400 people died. The structural engineer and architect were given 3 years each. So if it's meant to be an 800 thick column and you're on site as the construction engineer and someone says, oh, it doesn't need to be 800, make sure it gets built as 800. Okay? Make sure what's on the drawings gets built. And that was the Sampoon department store collapse. And you need to know how to draw a Benny moment diagram. And I'm going to show you an easy way to do it. We will leave that one for now. Benny moment diagram using singularity functions. So, shall we do that one? One more? We'll do one more. And then I'll show you the easy way. Now let's be clever. Okay, let's do it the clever way this time. You look at this, you go, I have to calculate my reactions first and make my cut. Let's be clever, because you're allowed to be clever. And let's say no, let's consider a free body diagram to the right. And if we consider that free body diagram to the right, do we need to know our reactions yet? No. So we're going to cut the beam. We have 20 kilonewtons here, 10 kilonewtons here. So this time round, we'll measure X effectively is this distance here. So what does that distance in there become? X minus 4. Now take moments at the cut. Now can you see I've drawn the moment this way as going clockwise, because that is what a positive moment will create, a positive moment. But when I come to equilibrium, all the moments at the cut equal 0. All the moments, bending moments equal 0. Let's take moments at the cut. I write that as minus m, because it is going clockwise. So I've got 2 point loads. A moment is force times distance. I have minus m. Then I have minus 10 times x minus 4. And my second load minus 20 times x, all equals 0. So nice this time round. Nice and simple. Now, but what you have to remember is when you consider a free body diagram to the right, x equals 0 is at the tip. And I've got my signs wrong. How come no one's called that out yet? Oh, you did, and I didn't hear you. So, just take that further away. M is equal to minus, minus. And why is it minus? I have a cantilever. Which side is in tension, the top or the bottom? The top. My bending moment has to be drawn above, and above is negative. Here's my expression for my bending moment. What does my BMD, my bending moment diagram, look like? When x is 0, what's my moment equal to? 0. This number in here is negative. It disappears. So in here, that term is negative. So when x is 0, m is equal to 0. Can you see here this is a linear expression? When x is equal to 4, what's my bending moment equal to? Minus 80. And when x is equal to 8, what's my bending moment equal to? I don't have a value here. Minus 160, minus 40, 200. Minus 200. So my bending moment diagram, oh, I'm doing a really bad drawing here. Looks like that. In this region here, m is equal to minus 20x. Now I have a moment here equal to minus 200. Guess what this reaction moment here is equal to? It's equal to 200. Because the moment in the beam is equal and opposite to the reaction moment. If I draw a little free body diagram in here, the moment in the beam is negative 200. What does that mean? It means a sad face. So I apply a moment like that because that causes a sad face. So my reaction moment here, this is my 200 or my negative 200. So my reaction moment here, assuming I'm 0.000001 mil away again, is equal to 200. So when you have cantilever systems, you can calculate the reaction moment and straight away you know the value of the moment in the beam. So I could have calculated that moment and said, okay, I know the moment in the beam is 200 as well. Okay, let's show you the easy way to do it. Again, don't think I can forget this. Lizzie calls this the hard way. You need to know how to come up with that expression for when we do deflections. Do you want to know a quicker and easier way? Yes. Okay. Fortunately, there is a relationship between shear and bending. Why is this fortunate? Because shear force diagrams were dead easy to draw, weren't they? So basically, once we have our shear force diagram, we can use that to help us draw our bending moment diagram. So how do we come up with this relationship? Free body diagrams and equilibrium. So we consider a small section of our beam, dx wide. We draw all our unknown internal forces on there. We've left out the horizontal one, okay, because that doesn't affect bending. We've put our load in on there, in this case our load W. So here we have our free body diagram here. From equilibrium, looking at all the forces in the y direction, we have V up on the left side. We have V plus dV down on the right side. Our load here, kilonewtons per metre, is W. So W times the distance dx is the load down. And from that, we get a value for W as related to slope. And what that is telling us is the load is equal to the slope of the shear force diagram. Now, what do I mean by that? I'm just going to jump back. Remember that load is equal to the slope of the shear force diagram. And I'm going to go back to where we drew this shear force diagram. Where is it? This one here. See this slope of this line here? What is the slope of that line? It steps up 50 kilonewtons over 10 metres. The slope of that line is therefore 50 divided by 10, which is 5. Our load is 5 kilonewtons per metre. If we go back to this other one back here, see my shear force diagram is sloping. What is the slope of that line there? Well, it steps down 80 kilonewtons over 4 metres. Rise on run is equal to hypotenuse. Yep. 20. My load here is 20. So that is why you have zero slope with no load. That's telling you you've got no load acting on there. Your shear force diagram is horizontal. When your shear force diagram is linear, the slope of that line is equal to your load. This is heavy going, I know, but this is cool maths. Okay, I think it is anyway. Come on, give me another 10 minutes. We'll do another 10 minutes and then we'll head out. Okay, looking now, taking moments at point A here. When you do take moments, looking at our moment expression, it's our force V times our distance dx. This blue term here, this is the fact that when you, when you have a uniformly distributed load, what do? We come up with the equivalent point load in the middle. So in this case here, W dx, and it's acting in the middle of that dx on 2. So we have this term in here. Now looking at that term, that's dx times dx, and dx represents a very small part of the beam. So this term here is so small we effectively ignore it. So now we have a relationship between shear and moment. The shear is the slope of the bending moment diagram. So when we draw the shear force diagram, we're actually drawing the slope of the bending moment diagram. So knowing what the slope is, we can draw our bending moment diagram. So we have this wonderful relationship between load, shear and bending. If you actually get your mathematical expression for your load and you integrate it, it gives you your shear. If you then integrate it again, it gives you your bending moment. That expression we get for our bending moment, if we differentiate it, it gives us the expression for our shear force. And differentiating it again gives us our expression for our load. So those three things are linked mathematically. So, let's look here. We had drawn this bending moment diagram. Here, our shear force is 0. Sorry, our shear force through here has a value of W on 2. So you can now say through here, the slope of our bending moment diagram is equal to W on 2. And the slope of our bending moment diagram in here is equal to minus W on 2. Let's have a look at that. Our bending moment diagram looked like that. Positive shear force, downward slope. Now some of you are sitting there going, what do you mean positive is downwards? Remember, we are drawing our bending moment positive down. Okay? So wherever you have a positive shear force, you know your bending moment is sloping down. When you have a negative shear force, your bending moment is sloping up. Shh. Now, V is equal to the m dx. So what's m equal to? The integral of V. Have a look at my shear force in here. It's equal to some constant, isn't it? In this case. When you integrate a constant, what do you get? Cx plus d, you get something linear. Whenever your shear force is constant, your bending moment will be linear. No questions, automatic. So how did we draw this bending moment diagram? We knew our bending moment was 0 at the two supports. We knew we had a downward slope because our shear force was positive. We know we have an upward slope because our shear force is negative. Join the dots. It's a dot to dot. You go, okay, I know it's 0 here, it has to slope down in a linear fashion, and then it has to slope up. So I can get the shape. The only thing left to get is what's that maximum value there? Well, didn't we say the bending moment is equal to the integral of V? What does it actually mean? Area under the shear force diagram. What's that area here equal to? P on 2 times L on 2, PL on 4. That was the value we got for the maximum moment. How good is that? You must like maths. That's why you're here. That is cool. Agree with me? Okay, let's look at our uniformly distributed load case. Shear force diagram, are you all happy with that? So, this is my shear force diagram, V, we call it SHF, but it's also equal to the slope of my bending moment. My bending moment we know is 0 at the support ends. My shear force is positive, that means it slopes down, then my shear force is negative, it slopes up. But this time round, the value is reducing. So what does that mean? It means the slope of my bending moment is reducing. And isn't that what it's doing now? It's a big value, it's getting smaller, and then my shear force, my slope is 0. So what does that mean? When V equals 0 or passes through 0, that corresponds to a maximum or a minimum value in your bending moment diagram. Let's go back here. What did our shear force do through here? Can you see it passed through 0? So wherever your shear force passes through 0, that gives you a maximum in your bending moment diagram. So once you draw your shear force diagram, which you can easily do, you have a go at drawing your bending moment diagram. And then you say to yourself, okay, What are the rules? This shear force is positive, it has to slope downwards. The shear force in here is negative, it has to slope up. The actual slope is big, it's getting smaller and smaller and smaller. So people here will try and draw, I'll get shapes like that for my bending moment diagram. And I say, does that agree with your shear force diagram? So all you have to do is you have to come back to your shear force diagram and say my slope is 25, then it's getting smaller and smaller and smaller. Here my slope is 25, it's getting smaller and smaller and smaller. It's 0, then it's getting bigger and bigger and bigger. That is cool. So, here is the full table that's in the online study guide. I've written page 106, I'm not sure if it is page 106. Have a look, this is a good table to memorise. Are you happy a point load gives you a step in your shear force diagram? So, the slope here has a big value and then it has a small value. My value of shear force here, it's a constant. So that means my corresponding bending moment is the integral of a constant, which is Cx. My shear force here has a value d. So my bending moment here is integral d, which is dx. This value of shear force represents the slope. Can you see how there's a sudden change in slope? Wherever you have a point load, you will get a sudden change in your bending moment slope. Let's go back here. Sudden change in the value of the shear force. Can you see the sudden change in the slope? It all ties in. If you do this in a logical manner, it will work. Your shear force now is linear. What do you get when you integrate a linear expression? A parabola. Your bending moment under a UDL load is a parabola. And remember this, it's always a happy parabola shape. For it to be a sad parabola shape, your loading will be applied upwards. When your loading is down, whatever parabola shape you go for, it's happy. We're not doing this one, so you can forget about that. The triangular load. An applied moment gives you a step. We're still 5 minutes early, but I said we'd finish at 10 minutes early. So please, 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 please go over that, because next week I'm going to do example after example. And it will make sense if you are familiar with the rules. Come and ask me questions now.